Hi everyone, so in this video I'm going to talk a little bit about Vmax and Km and use an example to illustrate how changing the enzyme concentration will affect Vmax but will not affect Km. So the first thing I want to do is to remind you that Km is equal to the substrate concentration at which your velocity is half of Vmax. Let's look at an example of what the Michaelis-Menten curve would look like for a given substrate concentration, and that's in millimolar, and an initial velocity, so this is V0. And I labeled this as V1, I just mean this is my first set of values that I'm going to show you for initial velocity, and those values are, in the units for that are millimolar per minute. So I'm going to show you what it would look like if I were to plot this using Excel. So this is the curve that I would get if I plot that data, and you can see that the Vmax approaches 20 millimolar per minute. So it's around here, right? So we actually never reach Vmax, but it approaches 20 millimolar per minute. So if I wanted to find the substrate concentration at which my velocity is half of that, then I would look at 10 millimolar per minute because that's 20 over 2. So if I do that, I can see that my Km is approximately, let's say, 0.6 millimolar. So that's my substrate concentration at which my velocity is equal to half of the maximum velocity. Now let's say that I double my enzyme concentration. So I took these values here for the first set that I show you, and I multiply those by 2. So that's what you see here. These values are just the first set of values I show you multiplied by 2. So now I'm going to show you what it looks like when I plot this data into Excel. So I have both of my curves here. This is for the first set of value I show you, where we saw that the Vmax approaches 20 millimolar per minute. And recall that if we wanted to determine the Km for that, we would look at half of the Vmax, so that would be about 10 millimolar per minute. And we would find the substrate concentration that corresponds to that. So that would be 0.6 millimolar. Now, for the second graph, I doubled the enzyme concentration. And as you can see, now my Vmax approaches, which would be around here, approaches 40 millimolar per minute. So as I doubled the enzyme concentration, my Vmax doubled. So now if I want to find the Km for this, I would look at half of 40 millimolars per minute, which would be 20 millimolar per minute. And if I find the substrate concentration at which I reach that half saturation point for the second graph, I see that that's the same. It's still 0.6 millimolar. And if you think about it, that makes sense because Km is a constant that is based on the rate constants for the formation of the enzyme substrate complex and the dissociation of the enzyme substrate complex. And what do I mean by that? So recall that for an enzyme catalyzed reaction, we have first the formation of the enzyme substrate complex, and this is a reversible reaction. And then we have the formation or the release of the product with the free enzyme dissociating from the product. So we have also rate constants that are associated to that. So this would be K1, and this one would be for the formation of the enzyme substrate complex. Then we would have K2 for the loss of the enzyme substrate complex, and this is also K3. So this is for the loss of the enzyme substrate complex as well. And so remember that Km is a constant that is based on these three rate constants. It's equal to K2 plus K3 over K1. So because all of these values are constants, Km is also a constant, and it will not change unless you do something to affect the affinity of the enzyme for its substrate. So for example, if you were to use a competitive inhibitor, that would affect your apparent Km because you would be affecting the affinity of the enzyme for its substrate. Otherwise, if the experiment that you're carrying out doesn't affect how well the enzyme can bind to its substrate, then it's not going to affect your Km.